Democratizing data sounds like a very big subject here. And what does it actually mean? So the claim of our company is that we make it possible for every organization to collect and evaluate marine data professionally. And that's a little bit how we feel about what does it mean to democratize data, because we make it affordable for people to actually generate data or receive data from other companies. And I think, and that's my sincere belief, that the basic principle of a working democracy with a capitalistic system somewhat connected to it is you have to offer your services at an affordable price for as many people as possible, because only then things will work out well. And so what we will focus on, and what I will focus on in my talk, is to talk a little bit about how we can bring down the cost of data and what steps need to be done, because I think automation and autonomy is a very important factor to bring down the cost in general. But what needs to be done actually to go from where we are today to where we will be in future. And so what we will talk about is, first of all, the complexity of marine data generation. So why actually is it so expensive? Then go dive a little bit into common sources for trouble. At Subsea Europe, we have a rental business. We're renting out equipment. I don't know, we have a turnover of rental equipment like, I don't know, 10 systems per month, maybe from the big multi-beam systems. And every time we ship out the system and we provide assistance during installation, or also when we receive the systems back, we see what can go wrong on that way. And that's, I've made a small compilation on that. So then I'll talk a little bit about standardization, or how I like to call it, lean data. I'll talk about the road to automation finally, and then the next exit, autonomy. So complexity of marine data generation. So what do we actually measure? So we measure a value. It could be depth sounding, it could be a temperature value, it could be a sound velocity value, but that value doesn't mean anything if you don't put a time to it. You assign a time to it, and finally you assign it to a location. So every time someone goes out and takes a measurement, they're measuring three things at the same time. They measure a value they want to measure, they measure it at a certain time and at a certain location. And I think you will go into this later on your talk about what time means to data generation. So I will not talk too much about it now. So values can be as simple as taking a tape measure to take a measurement from the seabed. Now I wait for the plane to take off. Does it take off, or? Yeah. Then timing. Timing doesn't only mean you have to put a time tag to your data. It also means there are certain times in the life of an offshore surveyor where data generation is not fun. So you can be at the wrong time in the wrong place easily. And the same is for location then. That's why I took this example of a MARTEC unmanned vehicle just about to go under a bridge, because there are certain locations where you have issues actually getting your precise location because you're facing GNSS outages or anything else. So how do we measure? We're using sensors. The easiest sensor I can imagine is just a tape measure, and we use platforms. So the easiest way actually to measure something would be, I am the platform, I take my tape measure and I go and measure how tall Daniel is. And if he was shrinking within the last maybe 5 to 10 years, which he did, I guess. Of course, in offshore surveying, we use a little bit more sophisticated sensors, and also the topic of our research is a bit more sophisticated than measuring how tall Daniel is. So we have multi-beam echo sounders, we have underwater positioning systems, we have navigation systems, which give us the attitude, like the position and the attitude of our measuring platforms. And we use cameras, and we mount those equipment on all sorts of different platforms, which could be huge research vessels or offshore installation vessels, which cost many 10,000 or even 100,000 euros a day. We're taking it on smaller and agile platforms. We take it on AUVs, we take it on USVs, we take it on ROVs, and we take it on sea gliders or permanent installations, as we will say later on. I forgot about the seabed observatory, sorry about that. So, under which conditions do we measure? That's also an important factor here. And you see a good example. I think that's actually a research vessel in not so nice surveying conditions, but still I think they're generating data because the platform is big enough, so the movement of the vessel will not affect the data quality too much. But if you take all this into account, and if you combine the complexity of the sensors you're using and the complexity of the platforms you put the sensors on, you will see that this actually makes marine data quite costly. Marine data is very, very expensive. And if you look at, for example, the efforts we put into generating data, and then you read articles about we know more about the surface of the Mars than actually about the deep sea, which I think is fake news, because yes, we have some high resolution images from Mars, but I think in total we have more data also from the deep sea than actually from Mars, but we can discuss that over a beer. Then you will see that actually generating data is a quite costly thing. So what are these common sources for trouble? Well, what do we see in our everyday work? And this can be missing or wrong pole and flange, missing wrong or faulty cable connections, faulty underwater connectors. We've just seen that. Survey workstation, PC is not working. This is mainly related to Windows updates, missing or wrong Windows updates. You have wrong firmware versions. Firmwares do not match. So you have the latest firmware in your PC or in your sensor, but you have an old software version trying to access the sensor. That doesn't work. You have wrong or inconsistent offsets. You have missing or faulty sound velocity sensors. Now talking about multi-beam, missing or faulty sound velocity profilers. You have a bad power supply and grounding earthing issues. So just to give you a few examples, like wrong flange. So flange can have the wrong shape. So that's an oval flange. And when you try to put on a round flange, like the standard 19-inch pipe flange, that doesn't work. So, or it's too flimsy. That's also a standard we see quite often when you go out. Look at this flange. I mean, this is a 19-inch pipe flange made from thick steel. It's not nice, it's rusty, that doesn't matter. You have those 8 holes in here. These 8 holes, they take in M18 stainless steel bolts. Each of these bolts can hold a few tons, I would say. I'm not a mechanical guy, so I would just say in total, you can actually put your boat on this, or even maybe this building on these 8 bolts. And then you see this. So it's not very clear on the picture, but I think this is like a 3-4 millimeter plate, while this is actually 6 or 8 millimeter flange. And then you have those bolts, you have a little bit of welding here. So that's what we see a lot. So the flange itself and the bolts are over-engineered. Then you have a transition piece, and this is too flimsy. Bringing me to the next topic, faulty underwater connectors. We can see here a little bit. Let me see. There's a little gap. This little gap is actually enough if the cable doesn't sit well and you have the system submerged over a very long time under a boat or on your pole in the water. It will end up in some upset condition, which looks like this. So we see that quite a lot. That's now an old style connector, which doesn't have a locking sleeve to actually lock this, but after a while, maybe 1 year on a boat, this could look like this. And then customers call and say, "Oh, the system's not working." So you can have issues with the sacrificial anodes. So when you take the system, when you get the system back and you see stuff like that, that's always a very bad sign. And you will find out that actually this is stainless steel. This is high-grade stainless steel we will see here, and still it's corroded. And the cause for this is that this is Eisenknocker, we call it. I forgot the English word, even though I'm a geologist, I should know. This is causing an oxygen minimum zone in this area. So the stainless steel couldn't build up the passivation layer. So what happens if it gets in contact with seawater is it's just corroding away. as any other steel. Very simple stuff here, wrong cable management. We have the standard cable meets cutter and cable meets door. That's what we see quite a lot. That's just a coax cable for the antenna. So each of these cables is around $200 US. So if you damage a cable in the middle, a 25 or 50 meter cable, you're not a happy camper afterwards. If you now take a sonar cable or a cable where you connect a complex sensor, the cable prices quickly exceed like 2,000, 3,000, 5,000 euros. And that's only the material price. Because what we're actually facing here is that time wasted, the sum of all potential sources for trouble can add up to many hours or days extra on the boat. So it's not so much the 2,000 euros for the cable, it's actually maybe more than 10,000 euros or 50,000 euros a day for the boat. Because when the system doesn't run, the boat cannot go out, it cannot perform the job. And you will sure pay the boat if you hire a boat. You will for sure pay the boat if you have a downtime on technology. And that's why standardization is so important on that. So you have real control over what's happening here. So this brings me to a very simple equation, and that's actually the equation we are building our business on it. We try to patent it and protect it, but it didn't work because it's so simple. So the amount of data generated is an equation of the number of sensors plus the number of ships times the time. Is that something we can agree on? Good. Brings me to the next step. Now I'm a commercial guy. I say, okay, then more sensors and more ships means more data in the same time or the same data in less time. Agree? Good. You should not nod all the time. That's it. If we now put into this equation, time means money, means more ships and more sensors, means more data at less money. Okay? But a ship and a sensor is also money. So if we now put in more ships and more sensors means more money, the equation doesn't work anymore. You can make a break-even calculation and see there might be a few, let's say, golden areas in your chart where you will actually still make money. But the point is, this only works when you have more ships and more sensors at less money, because only then you will get more data at less money. So how do we save money on ships and sensors? And importantly, without compromising on quality. And the first step here, what we learned over the past 1.5 years is standardization. Standardization is the very first step to actually get clean or good data. And we call it lean data. Because I like this summary from Ballet from the Lean Sensei. A nice book, a nice read, very short. The true potential makes taking the best performance figures due to exceptional circumstances and applying it to everyday work. So this scopes the work to be done, make the unpredictable predictable and the exceptional repeatable. So in other words, we as a benchmark, when we are a survey company, when we're providing services, our benchmark should always be this one perfect day we have in a year or in 2 years or in 5 years. And we have to measure ourselves and our performance on this beautiful, perfect day. And only then we actually tap our full potential. But in order to do this, we need to do things like standardization. So standardized work and standardized equipment are the fundament for lean data. So we need to document our current best practice. We need to standardize work and equipment. And this forms the baseline for continuous improvement moving forward. And what we actually found out over the last 1.5 years, you can actually, and it's like a miracle. You can start with real crappy standardized work. So you can have a process that doesn't describe anything, but you write something down. Like, for example, I want to mobilize a multi-beam system. You just say step number 1, mobilize the system. Step number 2, get it out in the water. So that's enough as a start. You know, you don't need to write a PhD thesis on that, because you go into this continuous improvement. So every time you follow these two simple steps, you will find out, ooh, there's something missing. I forgot cables, I forgot this, I forgot that, I need more duct tape, whatever it is. You put it in the list, you add it, and next time you've gradually improved. And if you go through these cycles over a period of a few weeks, months, depending on how many installations you have, you will finally, without doing any magic to it, you will end up at a pretty good and solid standard. And then you can dive into the very nitty-gritty details of getting out the last minute. So when we have a very beautiful day, we can mobilize our integrated hydrographic survey system, which consists of a high-resolution shallow water multi-beam system, a high-resolution inertial navigation system with dual antenna GNSS system, software, and everything. We can install it on a complete new vessel within 1 hour. That's our record. So we arrived, we put the equipment on, the flange was great, the cable could be laid easily. We had the offsets in place. We understood the offsets, which is also an issue from time to time because of the conventions and people talking like this. So, and it only took us 1 hour. When we were equipping these boats here, and we started on Monday morning very early, I think it took us almost 3 days to get this stuff up because it's new stuff, it's new equipment. We didn't have the right standards for that. So we wasted like 3 days. Fortunately, it was our boats and we reserved these boats, so the cost didn't grow, but still very important. So just to show you a bit of commercial. It's all about the money. So that was the integrated hydrographic survey system built on Arctosonic Sonic 2024 and the I2NS system. Comes in 2 boxes, and we've spent the last 1.5 years to actually optimize the workflow to get the system installed. So I think we're ready for the next step. We're ready to take the next step from automation, from standardization to automation, because as we stated, automation requires standardization. So precondition for automation is a tested and fail-safe standardized process. So we need to standardize the sensors and platforms. Here you see the system, not on that boat, but on a different boat. It's a standardized setup. We have the same setup on all the boats. We run the same cables. We have the same software running on all boats. And that actually brings us in a position that we can start standardizing our workflow from planning of the project to putting it on the vessel and to bringing it into operation and calibrating it. So the next exit for us then will be autonomy. And here an important factor is we need to differentiate between the autonomy of the platform itself. And you were talking about this, Arne, this morning during your presentation, and the autonomy of the sensor. And we've actually also, Arkadiusz, you named that, we've pointed out some issues with the platforms because we have regulatory issues here still, because there's no clear worldwide standard on how an autonomous vessel can be judged, if it's actually fit for purpose, if it can be sent out in a busy shipping lane, like the traffic separation area, for example, in the North Sea, where you see many, many big boats steaming in different directions. But at the same time, while bigger companies are solving these issues around getting the platform to a state where it can be approved by the global IHO or whoever is behind this and the local governments, we still need to think about actually bringing autonomy to the sensors. Bringing autonomy to the sensors, and we've also learned that from Arne this morning, has various layers. And it's not just like, okay, we make an autonomous sensor, here you are, and off you go. And Chris will talk a little bit about this later on to make it easier. actually bringing autonomy to the sensor means the sensor tells the platform what to do, and the platform communicates with the sensor what's currently happening. Only if you have this interaction between two separate autonomous systems communicating with each other, we can actually achieve true autonomy. And for multi-beam surveying, this would be, for example, you tell the system, hey, deliver me XYZ soundings, like 10 soundings per square meter for a given area and a given resolution. So if I want a real autonomous survey system, that's what I do. I just give an outline, say, hey, this is my box. I want 10 soundings per square meter, and I want to be able to have a resolve, I don't know, 25 centimeter object or half meter object. So and then the system goes out. The platform is taking care for the traffic and is taking care for the safety of navigation, and takes the line planning directly from the sensor, and the sensor is communicating with the platform, telling them, hey, this is what I need, and ooh, the weather has changed, we need to make a little bit narrower lines and things like that. That is true autonomy. And if we now bring this complexity in itself, you know, even if you do it in a simulated system, if you bring this together with what we've seen in the beginning of my little talk, faulty cables, faulty connectors, a lot of issues that are actually man-made, created by people, so you can avoid it by standardization. You see the complexity is huge, going from a standardized system or a survey system itself to a standardized system to an automated system and finally to an autonomous system. So, but there are some things we can do on our way. So we don't have to wait actually for everybody to be at the final stage before we can start stuff. And we've also talked about saving costs on our way. So how can what currently is available on the platform market and on the sensor market actually help us to generate more data at less cost? And one of this is the Mothership concept that we've created in cooperation with Nikola Offshore. And we're using here a manned survey vessel, the Mothership, which will be that beautiful platform you can see here, with a nice F deck and an A-frame, which will get some racks and launch and recovery stinger system for those little vehicles down here, which are the Martech T12 vehicles, fully electric. We will have a demonstration about this, a remote demo from Florida at 3 today, where we'll see about capability of these systems. And we're combining these, because if you put out one of these boats, this comes with a price tag. Let's just give it a price tag. We say 10,000 because this is what we want to get in an ideal world. Maybe this is not what the market is ready to pay for it, but in an ideal world, this is what we want to get. So 10,000 per day. Equipment, people, everything. Now this has a certain swath coverage you can achieve. So you have a certain time of a time window. Let's say we call it a weather window, okay? And within this window, you can achieve a certain square kilometer of profiles, because that vessel has a certain speed. So we're limited by the vessel speed, and we're limiting by the swath width of the vessel. So what can we do in order to get more data at the same time? We can bring in a second boat. So we're 20,000 euros a day. So we do double the work in one day, but at double the cost. So on the bottom line, we don't save anything. It doesn't change anything. It just changes something for me if my weather window, if my time window is very narrow, and the rest of the project is so very important. And I think you guys from dredging industry know that. You have a hopper or some big ship coming in, and you need to be ready with a pre-site survey before this big ship comes in, because the ship is so expensive. So you don't care if you just have a weather window of 2 days, or a window before the ship arrives, or a jack-up barge arrives. You don't care if the survey costs you 5,000 or 10,000, because you just want to get it done on time before this big 50,000, 100,000 euros per day ship or jack-up barge comes in. So that's where we are with this, let's say, step between automation and autonomy. If we now bring in those vehicles, and we believe we can have a USV or 2 USVs or maybe 4 USVs going out with a mothership, being launched by the mothership in the fields, in the area where it happens, and starting to survey the boring long profiles, which are very easy to survey. And while the mothership is on standby or also doing a job, so suddenly we are in the position where the cost for the vessel, for the platform is reduced, but at the same time, we still get more data. And that's where we want to be. That's the sweet spot. Now, Chris will later on talk a little bit about how we can increase survey speed on that, because right now, this would go out at 6 to 8 knots, depending on water depth, depending on ping density you want to have. Imagine what would happen if one of these boats, which are capable of going out to, I don't know, 35, 40 knots top speed, imagine those boats can go out and survey at 20 knots. So you do a survey at 20 knots with a mothership, and these little platforms here, the Mantis T12, will also survey at 20 knots because the survey system is capable of handling it. So we are reducing the amount of time by 1, 2, 3, 4, and then we're doubling the speed, so by 8. So by a factor of 8, lower cost, and that's really something that will change the industry, and that's something that we will start working on in 2022, and with the aim to have more ships, more platforms out at less money. To put it a little bit in perspective, and that's kind of my final slide before I go into a little bit of marketing spiel. So from sensor to system to full, from sensor system to full autonomy, we're talking about now 2020. We're in the middle of 2021. So we've roughly spent 1.5 years on getting this integrated sensor system up and running, on standardizing it, on making it work really smooth. We will now start in cooperation with Martech and Nikola Offshore to go into this combined platform and sensors, like putting a nice survey system, a nice sensor system on a nice platform. And then as the next step, we work on the integrated platform and sensor system. So we gradually increase the level of automation of all this, while we believe in 2024, 2025, we will see the first signs of autonomy on that in certain areas, which is again, maybe limited by legal implications. But since we have this mothership concept in our backbone, we will still be able to advance this technology and advance the workflows without compromising on performance. So that's why we have brought up a new slogan or a new claim. We call it the power of 3. So we put ourselves we will develop in a position where we can combine sensors and platforms into systems, and finally then into solutions. Questions?